Welcome back, everyone. So here we're going to draw a rational function, and the derivatives are given to us. So the first derivative is given, and the second derivative is given. So no need to compute them. We're going to use calculus to sketch this function. But let's go ahead and find out its domain first. So we know the domain of this function will be everything except when the denominator is not 0. So it seems like denominator will be 0 when x equals 2 or -2. So we know the domain of this function is -∞ to -2, open union, -2 to 2, open union to infinity. So everything makes sense except -2 and 2. So now that we know the domain, let's go ahead and find its asymptote. Because it's a rational function, we have a vertical asymptote. So the vertical asymptotes are when the denominator is undefined for the given function, and the denominator is undefined when x squared minus 2 equals to 4, because that's the denominator of the function here. So we set it to 0, and we say that x equals plus and minus 2. So we have two vertical asymptotes. Now we're going to look for its horizontal asymptote. So for horizontal asymptotes, we're going to take the limits. And once you take the limit, as x approaches plus and minus infinity of this function, x squared over x squared minus 4, you compare the degrees of this function. So the degree on top is a 2. So this is the highest power. And the degree on the bottom is also a 2. So because they're equal, we can say the horizontal asymptote is their coefficient. So this has coefficient 1, this has coefficient 1. So it's their ratio of their coefficients, that is 1. Therefore, we can say the horizontal asymptote is y equals 1. Okay, so now you should have a rough idea of how to sketch this graph, but let's go ahead and use a little bit more information from calculus to find where the function is increasing, decreasing, concavity, and inflection points, and also critical numbers. So first, we're going to grab the first derivative and find critical numbers. So let's go ahead and do that. So critical numbers of a curve is when the derivative is 0 and when the derivative is undefined or does not exist. So in this case, we take the derivative. So we know it's given to us, so no need to compute. If it wasn't given, then you would have to compute the derivative. So for this problem, we're given, so we're just going to go ahead and take that and set it equal to 0 and also test when it is undefined. So that's the derivative function. Set it to 0. So when I set this to 0, I only have -8x equals to 0, which means x equals 0 is a critical number. And then when is this undefined? The derivative does not exist when the denominator is 0, and that happens to be our asymptotes, the vertical asymptotes. So we take x squared minus 4 square, set it to 0, and you get x squared minus 4 equals 0, which again gives us the asymptote plus and minus 2. So these are also considered as critical numbers. Now let's go ahead and test the first derivative function. So you open the real line and draw these critical numbers and test the first derivative function. So here is 0, here's -2, and here is 2. So from -∞ to -2, we can test -3 into the derivative. Then -2 to 1, we can test -1. And then between 0 and 2, we can test 1. 2 to infinity, 3 is a good number. So plug them into the derivative and see if the result is positive or negative. So when I plug in -2 into my derivative, I get -8 times -2 over, so in the bottom is always squared. So whatever is in there, it's always going to be squared, so it's positive. So on top, I get a positive. So I'm sorry, I'm testing -3. Okay, so this is going to be positive. Here it's positive. When you do -1, you still get positive. When you plug in 1, you get negative. When you plug in 3, you get negative. So we can say that it's increasing. So f increasing from negative infinity all the way to 0, and f decreasing wherever the first derivative is negative. So that's 0 to infinity. So those are the interval of increasing and decreasing. Now, we should also realize that here, when we did the first derivative test, this is increasing and decreasing. So that means a local maximum at 0, 0. So let's go ahead and find that value. So when sign change from plus to minus, we have a local minimum. And if it's minus to plus, we have a local, minus to plus would be a local minimum. So since it's changing plus to minus here, we know we have a local maximum. So let's go ahead and find that local max value. That's going to be f of 0. Plug this into the original function. So the original function is right up here, this one. When you plug in 0, you have 0 squared over 0 minus 4, which is negative 4. So 0 over negative 4, we know that's going to be 0. So our local minimum value is 0. And now we can do the concavity test. So that's going to be on the second derivative function. So since it is given to us, we can just simply take it and test the second derivative function. So we'll do the same thing. We'll put it right here and see what are the possible inflection points are. So we take the second derivative, we set it to 0, and also when the second derivative does not exist. So if you set the top equal to 0, you have 8 times 3x squared plus 4 equals 0. You get 3x squared is equal to negative 4. Now this does not give you real roots. So there's no real roots here. So take the denominator. If you set that to 0, that's when the second derivative is undefined. In that case, we actually get the vertical asymptotes again. So we have x plus and minus 2 as our testing value for the second derivative concavity. So we have negative 2 and 2. Now we're going to check out the second derivative. So we'll do the same thing, pick a value each interval and plug it into the second derivative. Here, negative 3, here 0, and here 3. So plug in all these into the second derivative and see the sign. So when I plug in negative 3 in the denominator, I get positive, cubed, it's positive. On top, it's going to be positive. So this is positive. When you plug in 0, you get negative. And then when you plug in 3, it's going to be positive. Right. So if the second derivative is positive, we know that's where the function is concave up, and negative means concave down. So in this interval, we're concave up. Here, we're also concave up, and here we're concave down. So now let's go ahead and put the second derivative and first derivative all together. So here's the real line one more time. And we know that our first derivative, so let me just put this down there so it's easier for us to access. So here's the first derivative test that we ran. So our critical numbers were negative 2, 0, and 2. So let's split this up. And then we saw that it's positive to the left of negative 2. So here it's increasing. And then this is also increasing. And then from 0 to 2, that's negative. So it's decreasing. 2 to infinity, this is also decreasing. And now if you look above, that's the second derivative test. So we know that it's concave down from negative 2 to 0. So here, concave down, and then from 2 to infinity, concave up, and then negative 2 to negative infinity to negative 2, concave up. And we also saw there was a local maximum at 0, 0. All right, so now we're ready to almost put this down in a sketch. So let's draw the real line and the XY plane. Here you go. So first thing you want to do is label your asymptotes. So we know that for this problem, we had two. So we have two vertical asymptotes, negative 2 and 2. And we have a horizontal asymptote, y equals 1. Let's plot that first. So let's suppose this is negative a positive 2, sorry. Vertical asymptote, use vertical dotted line, and then at negative 2, another vertical asymptote right here. And then we have a horizontal asymptote at 1, so that's right here, horizontal dotted line. And then we have a maximum at 0, 0, so that's right here. So now let's focus on this interval right here. So from negative infinity all the way to negative 2, the function is increasing and it's concave up. So increasing is always something like that. And concave up is also along that way. So we know it's going to be increasing but concave up. It's going to look something like this. Now, of course, we wouldn't draw it this way because that's decreasing and that's concave down. So it wouldn't make sense. And then from negative 2 to 0, we're increasing and concave down. So concave down usually looks like this, like a set parabola. And that's also increasing and it's concave down. So we're going to go to that point right there, connect. And then from now let's focus on this interval right here. So negative 0, 0 to 2. So that's this interval right here, decreasing and concave down. So we continue to concave down and that's decreasing right here. So you can see that this is increasing and then this is decreasing. All right, so we got that figured out. And now for the last piece, again, you know the graph is either here or here. So we're going to use increasing and concavity to figure out. So we're decreasing. So decreasing is always something like this, and also concave down. That's also decreasing. So it's going to be this way or that way. And then concave up. So we know the graph has to look something like this. So that's decreasing and it's concave up. So concave up, you can think of it as a happy parabola on that side. So there you have the complete picture. So now try to match what we got on this green table along with the graph, so that way all of this makes sense. So here you can see there is a local maximum value, and where vertical asymptotes are labeled, x equals 2 and x equals negative 2, and the horizontal asymptotes right here, y equals 1. And pretty much that completes our sketching of this rational function.